Barnard star is one of the most intriguing stars in our cosmic neighborhood. At just 6 light-years away from our Sun, it is one of the closest stars to us, making it an exceptional subject for study. Despite being overshadowed by the Alpha Centauri system, which houses Proxima Centauri, the closest star overall, Barnard star holds its own distinction. It is the closest single star to our solar system, which makes it a prime candidate for examining the nature of stars and planets in our vicinity. A red dwarf with a remarkable history, Barnard star is estimated to be over 10 billion years old, which means it has been a witness to some of the oldest events in the galaxy. This ancient star is far older than our Sun, which is about 4.6 billion years old. With only 14% of the mass of the Sun, Barnard star is much smaller, cooler, and less luminous, emitting only a tiny fraction, less than 0.04%, of the Sun's brightness. This low luminosity makes it virtually impossible to see with the naked eye, which contributes to its obscurity in comparison to its more famous neighbors. Yet, despite its dimness, Barnard star is crucial in the study of stellar behavior, star formation, and planet hunting. One of the standout features of Barnard star is that it is a red dwarf, a type of star that is the most common in the universe, making up roughly 75% of all the stars in the Milky Way. These stars are known for their long lifespans, often extending into the trillions of years, far longer than our Sun's expected 10 billion-year life cycle. In fact, it is believed that no red dwarf has ever exhausted its nuclear fuel and died yet. The immense age and stability of Barnard star provide a fascinating glimpse into the distant past of the universe, giving astronomers valuable information about the early stages of stellar evolution. Red dwarfs like Barnard star are often relatively calm compared to other stars. While many stars, particularly more massive ones, are prone to violent flares and unpredictable activity, Barnard star is a notably stable object. This steadiness makes it an ideal target for detecting planets. Most stars, especially younger and hotter ones, emit strong flares that can interfere with the detection of exoplanets, especially smaller ones. The calm nature of Barnard star means that astronomers can study its surroundings with fewer complications from stellar activity. The proximity of Barnard star to our own solar system makes it a prime candidate for exoplanet hunting. In fact, its distance, only 6 light-years away, allows astronomers to use more precise methods of detecting planets than with stars that are farther away. Over the decades, astronomers have tried to detect planets around Barnard star, but previous attempts have mostly failed or been inconclusive. Still, Barnard star continued to captivate researchers due to its unique position in the cosmos. A key method that astronomers use to detect exoplanets is astrometry, which measures the star's position in the sky. When a planet orbits a star, both the planet and the star move around their shared center of mass. This causes a tiny wobble in the star's position, which, when measured precisely, can reveal the presence of an orbiting planet. This technique was used by astronomer Peter van de Camp in the 1960s and 1970s. He used astrometry to suggest that planets, possibly gas giants, might be orbiting Barnard star. However, despite extensive efforts, no such planets were confirmed. Further research, particularly in the early 2000s, began to rule out the possibility of large gas giants orbiting Barnard star. For example, a study in 2003 found no signs of planets the size of Neptune, and in 2013, another study confirmed that no planets larger than Neptune could exist within Barnard star's habitable zone. These results, while disappointing for astronomers hoping to find Earth-like planets nearby, nonetheless clarified the types of planets that could exist around Barnard star. Despite these setbacks, the search continued, and a breakthrough occurred in 2018. A team of researchers led by Ignacy Rebus used the radial velocity method, also known as the Doppler method, to detect possible exoplanets around Barnard star. This method works by detecting shifts in the star's light spectrum caused by the gravitational pull of an orbiting planet. As a planet pulls on its host star, the star moves slightly in response, causing its light to shift toward the blue end of the spectrum when it moves toward us, and toward the red end when it moves away. By measuring these shifts, astronomers can infer the presence of a planet and its properties, such as its mass and orbit. The results of the 2018 study were exciting, as they suggested the presence of a super-Earth-sized planet orbiting Barnard star. This planet, which was initially dubbed Barnard B, had an estimated minimum mass of 3.3 Earth masses, and its orbital period was around 233 days. The possibility of a potentially habitable world near our solar system captured the imagination of astronomers and the public alike. However, there was a catch. The radial velocity method, while highly effective, is not foolproof. The technique can sometimes be affected by the activity of the star itself, such as sunspots and magnetic activity, which can produce false signals that mimic the gravitational tug of a planet. This turned out to be a problem for the 2018 discovery. A 2021 study by researchers led by Lubin suggested that the 233-day signal, previously attributed to an orbiting planet, was likely caused by the star's own rotation and magnetic activity, rather than an actual planet. The story of Barnard star's potential planets took another twist in 2022, when a study using an instrument capable of measuring radial velocity in the infrared spectrum provided new insights. Infrared measurements are less affected by stellar activity, offering clearer signals for planet detection. The results of this study further suggested that the original 233-day signal was likely not caused by a planet, but rather by the star's own behavior. Thus, the mystery of Barnard star's planets seemed to persist. However, the story didn't end there. In October 2024, a new study using the advanced ESPRESSO spectrograph, installed on the Very Large Telescope, made a significant breakthrough. The researchers observed Barnard star 156 times over the course of 4 years, from May 2019 to July 2023, to collect precise data on the star's movements and search for evidence of orbiting planets. The ESPRESSO spectrograph is one of the most advanced instruments designed to detect tiny shifts in a star's position caused by orbiting planets. By analyzing the data, the researchers were able to separate out signals caused by the star's own activity from those that could be attributed to actual planets. The results of the study were promising. While the researchers did not find evidence to support the 233-day planet candidate from 2018, they discovered 4 strong signals, each with orbital periods under 10 days. The most notable signal had a period of 3.15 days, with a minimum mass of 0.37 times that of Earth, about 3 times the mass of Mars. This planet would have a nearly circular orbit very close to Barnard star, just 0.0229 Australian dollars away. While its small size and close orbit suggest it is likely a rocky world, the extreme heat generated by its proximity to the star makes it an inhospitable place. With an estimated equilibrium temperature of around 400 Kelvin, this planet is far too hot to support liquid water or Earth-like life. In addition to this primary candidate, the researchers found 3 other signals, which suggested the presence of even smaller planets, each with masses ranging from 0.17 to 0.31 times that of Earth. These planets, if confirmed, would also orbit close to Barnard star, making them too hot to support life. While the study in 2024 did not find any Earth-like planets in Barnard star's system, it nonetheless provided important insights into the types of planets that can exist around red dwarf stars. These discoveries are just the beginning, as the development of advanced telescopes like the Extremely Large Telescope, ELT, and the James Webb Space Telescope, JWST, promises to revolutionize the study of exoplanets. The ELT, with its giant 39-meter mirror, will enable astronomers to detect smaller, more distant exoplanets, while the JWST's ability to observe in the infrared will allow for detailed studies of exoplanet atmospheres and surface conditions. That's all for today's exploration here at Space Lab. Keep looking up, and who knows what we'll discover next.